Hello, Year Nines. We are going to study about sound waves today and the structure of the ear. So as per the specification, what you need to know is describe with examples the processes which convert wave disturbance between sound waves and vibrations in solids. Then why such processes only works over a limited frequency range and how is this relevant to human hearing. And then how the changes in velocity, frequency, and wavelength in the transmission of sound waves from one medium to the other are interrelated. Actually, the last bit, PF.1 F, we have already done that as a refraction before. So we'll be covering the first 2 points in today's lesson. So from the beginning of waves itself, you are already aware of the two types of waves, transverse wave and longitudinal wave. And when we did the examples for transverse waves and longitudinal waves, we said light wave is a transverse wave, or all electromagnetic waves are transverse waves. And we said that sound wave is an example for longitudinal wave. So sound waves are longitudinal waves. And what does that longitudinal waves mean? Again, some very basic stuff about sound waves. How does sound travel? In order for us to produce any sound, we have to make an object vibrate. So sounds are produced when an object vibrates. Then so when that object is vibrating, in front, the air particles in front of it or any particles in front of it will be made into a compression and rarefaction, which then get transferred along and then reaches our ear. So in short, any object has to first vibrate in order for it to produce a sound. Then through a medium, it reaches our ear for us to hear it. So different examples, violin strings, drum skin, voice box. How do we talk? We produce sound. We produce sound through the vibration of our vocal cords. Loudspeakers, through the vibration of the loudspeaker cone, it produces sound. So it is basically an object has to vibrate in order to produce a sound. Then what happens once it reaches our ear? This is a very important part of the topic, and you need to know the functions of all the parts that we are going to mention now. So the first thing, so we said something is creating a sound. Say somebody is playing violin. The violin strings are vibrating. It creates compression and rarefactions in the air in front of it. And then that sound waves are being collected by our earlobe or pinna. So the purpose of the earlobe or the pinna is to collect the sound waves. Then you can see it is going in this direction, isn't it? So what do we have there? We have the ear canal. So the sound waves that has been collected by the earlobe or the pinna is traveling along the ear canal. Then it reaches our eardrum. It is this bit that you see here. It reaches our eardrum. It makes our eardrum vibrate. Okay, so far the sound waves are collected by the earlobe, then it travels along the ear canal and then finally reaches our eardrum, which is marked as position 3. Then what happens? Can you see these small bones attached here? One second, I will just change my pen. Okay, can you see the bones here? The small bones. Those small bones are called the ossicles. Since they are very small, when we make and they are attached to the eardrum, when the eardrum vibrates, they also start vibrating. But when they start vibrating, because they are much smaller in size, now in this slide, it's just a table highlighting the main functions of the different parts of the ear. So either you can pause the video here, write this down, or I'm pretty sure previous slide itself when I was explaining the things, you would have written it down or tried to copy it. Otherwise, this video is there. If you go to YouTube, we have a YouTube channel for physics there, Nonsuch World of Physics. So if you go there, if you go to YouTube and search for Nonsuch World of Physics, and if you look in the year 9 playlist, this topic should be there. So it is available to you anytime you want to go back and refer or make any notes. So these are just the main highlights of the different parts of the ear and their function. So we are moving on to the frequencies, different frequencies of sound that we can hear. The range of frequencies of the sound that you can hear is called the hearing range. So can we hear from any frequency we want to any frequency? No, we can't. Can we? There is a particular range of frequencies that we can hear. Which is that range? Who knows the answer for that? I can give you 30 seconds to discuss that answer. What is the range of, or what's the human range of hearing? So your 30 seconds starts now. Now, when we talk about the range, or the range that we talked about in the previous slide, do all of us have the same hearing range? No. It says that around 1 in 5 people suffer some sort of hearing loss, which can be temporary or permanent. Temporary is the one that, it's like we develop ear infections as a part of a cold or fever or something like that. But then we will recover after that. Permanent is where from birth there will be that issue, or later on had some accident or something happened because of which a part of the ear is damaged, or sometimes it gets severely infected and then that damage can happen. Okay. Sorry. Other than that, as people get older, as I said before, their ability to hear that high frequency end becomes weaker and weaker. So which end of the hearing range will be affected? They won't be able to go up to 20 kilohertz anymore. It becomes shorter and shorter. Okay. Now in the next couple of slides, we are going to see two main properties of the sound waves, which is again a very popular question of the examiners, a topic of the examiners, but at the same time, it's a very easy one also. So the first property of the sound waves we want to see is the loudness and its amplitude. So the loudness of a sound is related to its amplitude. Sound can be loud or quiet. So how can we see whether the sound is loud or not? I'm saying how can we see, not hear. For that, we have an oscilloscope. An oscilloscope is something that shows us the waves. So the loudness of the sound wave is shown by the height of the wave. And you already know that the height of the wave is called amplitude. So an oscilloscope will have a screen like this. And on that screen, you will be able to see a wave. So if you look at both of them, you can see the height of the wave is different for both of them. So if you look at the first wave, this is the height. And if you look at the second wave, this is the height. So the second wave is louder compared to the first wave. Why is it louder? Because it has a bigger amplitude. So be careful with the keywords. It is louder because it has a bigger or larger amplitude. Okay, amplitude is a volume sort of thing. So on an oscilloscope trace, the larger the amplitude of the trace, the dash the sound will be. What can be the keyword we use there? Larger the amplitude, louder the sound. So the sound is going to be louder. Okay, so one property is loudness and amplitude. Next. So the next property, the second property, is the pitch of the sound and how is it related to the frequency of the sound. So pitch or frequency means high or low. A high pitch, low pitch, that is what you call the pitch. So now in your books or on your lined paper, you can sketch a few shapes of the graph. So the first one is a loud, a low pitch sound. So the loud means it should have a high amplitude. Low pitch means it should have less frequency. So I'm going to do the first one for you, and then the rest you can do on your paper. So a loud means I'm going to go for a higher amplitude. I'm drawing on the screen, so mine would not be that, drawings might not be that perfect. And low pitch. So I have only 1.5 waves there, isn't it? So it can be a low, it can be considered as a low pitch. Now for the next couple of them, when you're drawing, you have to compare it with the first one. So a soft means it is not that loud as mine, the first one I have drawn. So the amplitude should not be as big as this. High pitch means you should have more number of waves. So I'll ask the miss to pause the video for you to give you 2 minutes to figure it out, and then I'll show it on the board. So please, someone who's in the class, can you pause the video for the students, please? So I hope you have figured it out. So the second one is a soft one, but at the same time it is a high pitch. So soft means it should be having less amplitude than the other one. High pitch means it should have more waves. And as I said, I'm drawing it on the screen, so my waves are not the best of the ones. Then a loud means, again, high amplitude and high pitch. So you should have something like this. So this is how they'll ask you to compare the loudness and the pitch. Another thing is, say they have given you a wave like this. Sorry, and then they're asking you to draw a high pitch wave. When they're asking you to change the pitch, please can you make sure that you're changing only the pitch. So the next one you draw should be like this, which means you have changed only the pitch, you have not changed the amplitude. Do you get what I said? So if I just redraw that once again, when they are giving you a wave, and so they had given you a wave like this, and they're asking you to make it a high pitch wave. So when they're asking you to make a high pitch wave, what you need to keep in mind is you're changing only the pitch, which means your height of the wave should be the same. Okay, so most of the time they ask you to show it on the same graph. So only change what they are asking you to change, don't change anything else. Okay. And the last thing you need to know is, how does the speed of the sound change in different materials? So you know that sound travels by making the particles vibrate. So what do you think? If the particles are more closer together, will the sound be traveling faster or slower? More particles together means it is easier for it to transfer the vibrations, right? And in which state of matter do we have all the particles very closely packed? We have them in solids. So in solids, since the particles are very closely packed, sound waves will travel the fastest through solids. So keep that in mind. Sound waves travel the fastest through solids. It is opposite to electromagnetic waves. Electromagnetic waves we said when it enters a more dense medium, it slows down. Sound waves are opposite to electromagnetic waves. It travels the fastest through solids. Why do they travel the fastest through solids? Because the particles are closer together, which means vibrations are more easily passed from particle to particle. These are the key words in your answer. Please don't miss those key words when they ask you why sound travels the fastest through solids. The particles are closer together and bound tightly, so the vibrations can move more easily or passed more easily from one particle to another. So these are the things you need to know about sound waves. We need one more lesson on ultrasound that we will do next lesson. So as I said before, anytime you feel like you need to go back into this lesson, or those who have missed today's lesson, this is a link, this is a video you have to go through. It is there in our Non-Such World of Physics Year 9 playlist. If you look, it will be saved under the title Sound. Okay, I hope I have done some justice to the topic and you were able to understand the topic. If not, when I see you again next lesson, you can ask me any questions you have. Okay, see you.